The Earth's surface is curved, but as long as the areas we study are small, let's say no more than 100 kilometers across, it is acceptable to think of the surface as flat. We analyze maps, measuring areas or distances from maps rather than from the real world, and performing various forms of analysis and modeling. We examine images of the Earth's surface from satellites, even though those images must be distorted if they're shown flat. But when the study area is large, we definitely need to worry about the curvature of the surface and the distortions that are introduced whenever that surface is captured on a flat map. Sometimes the distortions are very significant, and their effects can be surprising. How often are airline passengers puzzled when a flight from North America to Europe is shown curving north over Greenland and Iceland? Why don't they just fly a straight line? Or when a flight from Seattle to Hong Kong spends most of its time over land, over Canada, Asia, Siberia, and northeastern China. Or when a flight from Dubai in the Persian Gulf to San Francisco flies very close to the North Pole. There are many map projections or ways of distorting the Earth's surface so that it can be portrayed on a flat map. Some are designed to preserve area, so that the areas measured from the map are proportional to the true areas on the Earth's surface. Others are designed to preserve distances from some point of interest, such as a home location. But no projection can preserve all areas and all distances. Two useful principles emerge from this. First, it is impossible to lay a raster, such as a remotely sensed image, on a curved surface. So every flat visualization of such an image must involve the distortion of a map projection. Second, it is impossible for any map to have an exactly constant scale. Here is one example of extreme flattening, a view of the Earth's surface using the Plaque-Carré projection. It is often termed the unprojected projection because it simply maps longitude on the x-axis and latitude on the y-axis. The entire upper edge of the map corresponds to a single point on the Earth, the North Pole, and the bottom edge is occupied by the South Pole. The left and right edges correspond to longitude 180. In reality, of course, none of these four edges exist on the continuous surface of the Earth. It would be very logical at this point to ask why GIS designers chose to build software to process flat maps rather than globes. There are several reasons. First, the maps and images that populated early GIS were already flat, and most applications focused on small areas with little distortion. Second, processing data on the curved surface requires the use of more complex mathematics, specifically trigonometric functions, which are comparatively slow, and early designers were conscious of the need to process large quantities of geospatial data using the limited computing power that was typical of the 1960s through 1980s. Third, computer screens are flat, and it was not until the 2000s that graphics processing capabilities of personal computers allowed software to display and manipulate three-dimensional objects, thanks largely to the video gaming industry. Finally, the only way to display all of the Earth's surface at once is to flatten it. In the past quarter century, many GIS scientists have been intrigued by an entirely different approach to mapping large areas, using what are known as discrete global grids. They treat the Earth as a continuous surface, and they subdivide the surface hierarchically into smaller and smaller elements, allowing the user to zoom from very coarse to very fine detail. They also provide a convenient basis for sampling the Earth at uniform density. One of the first popular implementations was Google Earth, which was released in 2005 and became instantly popular. There are many distinct discrete global grids, but all are hierarchical and avoid the problems with the poles on longitude 180. One of the simplest starts with an octahedron, oriented so that the poles occupy two of the vertices, and the other four vertices are arranged around the equator at longitude 90 east, 180, 90 west, and 0. Number the 8 faces 0 through 7. Each triangle is divided into 4 by connecting the midpoints of its 3 edges. Number these 0 through 3. Each of these smaller triangles can then be divided into 4, and the process can be continued ad infinitum. Subdividing about 20 times will zoom down to a spatial resolution of about 1 meter. Moreover, any triangle at any level of subdivision can be identified as one base 8 digit, followed by a string of base 4 digits. The use of triangles and the numbering system are particularly well adapted to today's graphics processing technology. So if discrete global grids have such significant advantages, how come they have not replaced the use of map projections in GIS? Again, there are many reasons. First, there are many DGGs to choose between, with their own advantages and disadvantages. Second, the geospatial community is heavily committed to map projections and to practices that fit the specific needs of specific disciplines. For example, people who work in the physics of ocean circulation like to use grids that become finer close to coastlines and coarser in the open ocean. Third, any switch to discrete global grids would be highly disruptive, and while it would open entirely new areas of research, the costs of the training needed to adapt to the new technology would likely exceed the benefits. The legacy of past practices can be an enormously important factor in the application of any technology.